Alright, everyone. Since my TA is a little bit late, we're just gonna start right now to keep you guys from waiting. So today we're gonna cover congruence and similarity.
什么？
So what does the word congruent mean? Well, it's an adjective, and in general it means in agreement or harmony. But in geometry, it's gonna mean identical or equal in shape. And similar, it's an adjective. It means resembling without being identical, but in geometry, it's gonna mean that they have the same shape with the same angles, and there's gonna be a proportion between them, but they're not necessarily gonna be the same size. So, well, here's an example. So these two triangles are congruent, as you can see, because they're exactly the same in every way, while these two triangles are only similar because while their angles are the same, one's a scaled up version of the other, so they're not exactly the same, so they're similar. Alright, so now we're going to go over the actual definitions of these two words in geometry terms. So two shapes are congruent if all their angles and all their sides are equal. It basically means that if it's a shape and you just move it somewhere else, or you rotate it or flip it. And similar, it means that they have the same angles, but they're just scaled differently. So for example, one shape might be a scaled up version or a scaled down version of the original. So based on these definitions, congruence is actually a more specific form of similarity, because you can tell that if they're congruent, it basically means that it's scaled by a ratio of 1. So it's both similar and congruent, but so all congruent shapes are similar to each other, but not all similar shapes are congruent to each other. Alright, so here's a quick question. I'll give you guys like maybe 1 to 2 minutes to do this one. Alright, I think it's been enough time, so now I'm going to reveal the answers. So 1 and 3, they're actually congruent because, as you can see, 3 is just if you rotate one a bit, yeah, you just rotate one a bit to get 3. And so next, 2 and 2, they're actually similar because, as you can see, although they're like the same shape, the 2 on the right is actually a smaller version, so they're similar, but not congruent. now 3 and 4, the black line means that there's nothing special between them, because as you can see, the one on the left, number 3, it's not a full circle because the middle part of it is gone, and while on the right it's a full circle, so they're not it's not similar or congruent. And finally, for 4 and 1, they're actually congruent because one is just like a slightly rotated version of 4. All right. So I hope some of you guys have sent me your answers, and they're pretty good. So good job. All right. So now we're going to move on to ratios. So we can use ratios to find the relationship between similar shapes. So first, we're going to use it to determine if they are similar. So first of all, if the ratios between the sides are the same, then they're similar. In this example, we're using triangles, because it's the easiest shape to make an example with. So the first triangle, its sides have a ratio of x to y to z, and the second one also has the same ratio. So they have the same. The ratio between their sides is the same, which means that they're similar triangles. And yeah, but the thing to notice is that yeah, like the angles have to be the same between the two triangles. All right, so the next way, we can also use ratios to figure out how much one figure is a scaled up or scaled down version of the other. So it's not just figuring out if they are similar, it's figuring out how they are similar. So the first triangle, it has 2x, 2y, and 2z as side lengths, while the second one has x and y and z. So as you can see, each of the side lengths in the first one is twice of the smaller one. So the first one is scaled up, so it's going to be 2 times, it's going to be a 2 times version of the smaller one. And if you're not sure, always use ratios. So here's another question. I'll give you guys 1 to 2 minutes to do them. So first of all, you're gonna figure out if these triangles are similar, and if so, what the ratio between their sides is. Alright, so I think it's been enough time, so now I'm going to go over the answers. So for the first question, the answer is no, because when you try to find the ratio between the sides of two triangles, they're not equal. For example, the smallest side, it's 0.05 on the triangle to the left and 40 on the triangle to the right. So you would have to multiply by, I think 800 times to get to the one on the right. And if you try that for 0.1 on if you multiply by 800, you get 80 instead of 50, so that's not going to be correct. Alright, so for the next one, the correct answer is yes, the ratio is 1 to 1.1, because when you multiply each of the side lengths on the left by 1.1, you get the side lengths on the right. And for the third one, the answer is yes, it's 1 to 5, because on the left, you can see that the radius is 1, and on the right, it's 5. So you're multiplying by 5 to get the radius of 5. And also, these slides are kind of not accurate because, well, you can see that, for example, on the last one, the one with radius 5 is actually smaller than the one with radius 1, but, like, yeah, that's not that big of a problem, hopefully. So now we're gonna figure out how to find congruency in triangles. Well, if you know that to find if two shapes are congruent, you don't exactly have to know that all the sides and angles are the same. Because, for example, the question may not actually give you that much information. So there are some ways to find out if two triangles are congruent without needing to know every angle or side in them. So, well, if you're only given some specific information, how would we be able to know if two triangles are congruent? Well, with certain configurations of information, we can. So, these are some combinations of information where you can determine if two triangles are congruent. So, if they give you all three sides, we call that side, 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 or SSS. If you have a side, an angle, and a side, also called SAS. The important thing to note here is that the angle has to be between the two sides. And that's why it's SAS, because ASS or SSA, they're different things, and they're not good enough to determine if two triangles are congruent. There's also ASA, which is angle, side, angle, and so the side has to be shared between the two angles. And finally, AAS, where the side is only part of one angle. And there's also a special case for right triangles. It's HL, or also called hypotenuse-like theorem. So we're going to go over these more in depth on the next slide. So three congruent sides. So this means that if you know the three sides of both triangles, and you can like easily tell if they're the same, like if the side lengths are equal. If you have that, then you know that the two triangles are congruent. Also, same thing. If you have the same side, angle, and side in two triangles, then you know they're congruent. So for example, if you have a triangle with side lengths of, let's say, 2, 3, and or like, I'm sorry, let me go. So if you have both triangles have a side of 2, an angle of 30 degrees in between, and a side of 4, uh, then you should know that they're going to be congruent triangles. And then ASA, it's the same thing. If you know the angle, side, and angle, and they're the same between the two triangles, then they're going to be congruent. And finally, for AAS, if the two angles and the side they give you are the same for two triangles, then you know they're congruent. So here's a more detailed view. So as you can see, SSS, if they give you all three sides, then you know that they're going to be the same. If you have a side and angle in between and the side, you know they're going to be congruent. Also, angles, see, as you can see, the side that's shared by the two angles, if they give you the measure of the angles in the side length, then they're going to be congruent. And finally, they give you two angles and a side that's not shared, and then you know that if they're equal, then the two triangles are going to be congruent. And for the angles, the reason why only two is sufficient is because you know that all the angles in the triangle have to add to 180 degrees. So if they give you two angles, you can easily find the third. And then if they give you a side length, then you can lock in on the exact scale of the triangle. So you'll learn later that just having the three angles, that's not enough because it can be scaled up or down. So yeah, here's the a more specific view of the hypotenuse-like theorem. So it's only for right triangles because, well, hypotenuse, that's only used in right triangles to refer to the longest side. So if two right triangles have the same hypotenuse and have the same leg, then you know that they're equivalent. And that's because you can use the Pythagorean theorem to find the third side. And then after that, you just have SSS, which is side, side, side. And that's also, you already know that that's also a way to know if two triangles are congruent. Yeah, so as it said, if you use the Pythagorean theorem, you can find the third side, and then you can just use SSS. All right, so now we're going to move on to similarity in triangles. So similarity is a lot less strict than congruence because it doesn't have to have the same side lengths. As long as the ratios between the sides are the same, like it just has to be a scaled up or down version. So all the congruent theorems can be worked to determine similarities because, well, congruence is a more strict version of similarity, but instead, the side lengths don't have to be equal. It's just that the ratio between the corresponding side lengths has to be the same. And there's also three new ways. So if you just have angle, because then you can just determine the third angle, and then if you have the three angles, you know the shape of the triangle. The shape of the triangle is determined by the angles, and then it's just a matter of scaling it up or down. But it's similarity and not congruent, so that's allowed. And side angle side, which we also included in congruence, and side side side. So just remember that in similarity, um, the sides, they don't have to be equal between the two triangles. Instead, it's more like the ratios between corresponding sides have to be equal. All right, so here is some going over the ways to determine if two triangles are similar again. So if the two angles, if they give you two angles, then you know they're similar triangles. Also, if you have two sides and an angle in between, and then finally three sides. All right, so I'll give you guys a 10-minute break before going on to the golden ratio.
Wait, we get a 10-minute break, right?
Yup, we get a 10-minute break.
Yay.
Alright, so break time is over. I hope you guys enjoyed your 10-minute break. So now we're gonna continue on with teaching. So you may have heard of the golden ratio, which is an irrational number denoted by the symbol phi, and it's equal to 1 plus the square root of 5 all over 2. And so, but it's approximately equal to 1.618. And on the right, you can see the ratio between the side lengths of this rectangle is the golden ratio, and we're going to derive it using this rectangle later. So it's extensively used in art and architecture, and that's because it looks natural and is pleasing to the eye. So we're going to derive it. So how is it derived? And here are some examples of where the golden ratio naturally occurs. It even occurs in nature, and well, all of these photos were probably taken because, well, they look pleasing. So yeah, I'll give you guys like a couple seconds to look at these. Alright, so now we're going to derive the golden ratio. And to do this, we're going to derive it with a golden rectangle. So the golden rectangle, it's a shape that has a property called self-similarity. And that's because if you remove a square from the rectangle, like such that it's still a rectangle, you'll have another golden rectangle because it'll just be a smaller version of the whole thing. So the golden ratio, it's equal to the golden rectangle's longer side divided by the shorter side, and that's also equal to the ratio between the sides of the golden rectangle. So it has many other properties other than just being a way to derive the golden ratio, and so it's always been studied since the Babylonian times. So now we're going to derive it. So let's have the rectangle with sides A and A plus B, as you can see. And so because of that, we're gonna have another rectangle with sides A and B. And from the definition of the golden rectangle, we know that these two shapes are similar. So the ratios between their two sides are going to be similar. So we have that A plus B divided by A is equal to A over B. And we get this from the ratio between the sides of the rectangles. So for example, for the big rectangle, the longer side is A plus B, and the shorter side is A. So that's how we get A plus B over A. And then for the smaller red rectangle, we have that the longer side is actually A, and the shorter side is B. So that's where we get this equality from. And then if you multiply both sides by AB, you can see on the right, you get that AB plus B squared is equal to A squared. So if you subtract AB and B squared from both sides, you move everything to the right, and then you solve for A in terms of B. And you do that using the quadratic formula. So you get that A is equal to B plus or minus the square root of B squared plus 4B squared over 2. And then you can combine B squared and 4B squared into a 5B squared. So the square root of that is going to be B root 5. So A is going to equal B plus or minus B root 5. So A over B, which is the ratio, which is the golden ratio, it's going to be B plus or minus B root 5 over 2, and the whole thing divided by 2. So you would actually get 1 plus or minus root 5 over 2. But the reason why we don't consider 1 minus root 5 over 2 to be the golden ratio is because, well, root 5 is greater than 1. So 1 minus root 5 over 2 is going to be negative. And that doesn't make sense because, well, all these lengths are positive. So how are you going to have a negative ratio between lengths that are all positive? So that's how you derive that the golden ratio is 1 plus root 5 over 2. So now we're going to move on to something called indirect measurement. So it's a way to use similar triangles to find side lengths that we don't want to directly measure. So for example, in the real world, it's used to measure the heights of tall trees or mountains. And you can probably see why you wouldn't want to directly measure them because, well, first of all, like you would have to either like have a really tall ladder to climb up to a really tall tree, which is pretty obviously unsafe and dangerous. And also mountains. It's probably not a good idea because, well, first of all, like mountains are difficult to get on top of, and also directly measuring their heights, how are you gonna do that? Because, well, you can't really measure it. You can't really stick like a ruler that's perpendicular to the ground because the mountain's gonna cover up the point, like the point you're standing on when you're on top of the mountain. The point on the ground that's perpendicular to that, you can't really place a ruler there because it's covered by the mountains. So it's a very useful technique. And so here's a question. I'll give you guys 1 to 2 minutes to do it. So if Jonathan is 6 feet tall and he casts a shadow of 8 feet, well, and if what's the height of his dad? If his dad will cast a shadow of length 12 feet, and assume that the angle between the person and the sun's rays is the same for both people. Alright, now I'm going to go over the answer. So, you can see that they're going to create similar triangles. If you envision it, Jonathan and his father are both going to be legs of a right triangle. The shadow is going to be the other leg, and because it's along the ground and they're standing perpendicular to the ground, and the hypotenuse, well, that's going to be created by the sun's rays. So, and then the ratio between corresponding parts of their similar triangles are going to be equal. So, the the ratio between the lengths of the shadows is obviously 12 and 8, and then so their heights, that's going to be equal to the ratio between their heights. So since Jonathan's dad casts a shadow of 12 feet, so let's set his height as x. So 12 divided by 8 is going to be equal to x over 6. So if you multiply both sides by 6, you get that x is equal to 9. So Jonathan's father is going to be 9 feet tall, which is, wow, I mean, that's pretty cool, you know? It's pretty surprising. Alright, so next, we're going to move on to something called the splitter theorem. So, as you can see, it basically states that a line segment in the triangle that is parallel to one of the bases is going to form a similar triangle. So, as you can see in this diagram, MAN is going to be similar to BAC, and you can do that using angle, 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 because, well, first of all, they both share the angle A because, well, obviously BAC is going to be equal to MAN, and then ABC is going to have equal measure to AMN, and that's because MN and BC are parallel, and so in this case, AB is going to act as a transversal. And so they're going to be equal angle measure. And the same thing is going to go for ANM and ACB. So by AAA, you can see that these two triangles are similar. And so it basically means, well, you can just tell that the ratios are going to be similar here. So AM divided by MB is going to be equal to AN divided by NC. So using this, we can find the ratio that this line parallel to the base divides these two like other sides of the triangle into. So I'm gonna give you guys a question. Since it's pretty easy, I'll give you guys 1 minute to do it. So what is the ratio between the lengths of AM and MB if MN is a midsegment? So we covered mid-segments in the triangles chapter, so I hope you remember. Alright, it's been enough time, so I'm going to go over the answer now. So, well, you know that based on the definition, MN is it's a mid segment, so it splits AB in half. And so then AM is equal to MB. So the ratio between AM and MB is going to be 1-to-1. And so quick question now, guys. So what would be the ratio between the lengths of AN and NC? I'll see if you guys can do this within like 30 seconds, because you should be able to. Alright, some of you have given me the correct answer. So the correct answer is also 1-to-1 because, as you can see on the right, the ratio between AM and MB is going to be equal to the ratio between AN and NC. So since the ratio between AM and MB is 1-to-1, so is the ratio between AN and NC. And finally, this is the last theorem for this class, like for today's class, I mean. So the angle bisector theorem. So it states that the ratio between the two segments that an angle bisector creates on the other side. So you can see that in this triangle, the angle bisector splits the side opposite it into segments of length x and y, and so a over a, the ratio between a and b is going to be the same between the ratios of x and y. And an easy way to remember this is that a is just above x and b is just above y. So the ratios between them are the same. And you can also think of it as a over x is equal to b over y. And you can get this by dividing both sides by x and so if you divide both sides by x and multiply both sides by b, in the equation to the right, like a over b equals x over y, you get that a over x is equal to b over y. So here's a quick question. Given that AD is an angle bisector, find the length of BC if AC equals 5, AB equals 6, and CD equals 3. Alright, I think it's been enough time, so I'm gonna go over the answer. So, using angle bisector theorem, you have that, um, AC over AB is equal to CD over BD. So you get that 5 over 6 is equal to 3 over BD. So solving for BD, you get that BD is 18 over 5. And well, some of you might have been tricked because it's asking for the length of BC. So you have to add the length of BD to CD. So you're going to find that the final answer is 33 over 5. And that's equal to 6.6, which is an equivalent form. Alright, so here's the last question for today's class. So given triangles DAR and KMR, find the length of y. Alright, so I'm going to go over the answer now. Alright, so since DAR and KMR are similar by angle, you can see that DRA is shared between the two triangles, and you can see that MKR is the same as ADR, and the same thing with KMR and DAR. So using ratios, we have that, okay, yeah. So we have that y over y plus 11, which is the ratio between the side, their left sides, is going to be equal to the ratio between their right sides, which is 14 over 14 plus 16, which is 30. So if you solve for y, you get that y equals 77 over 8, and that's going to be the final answer. So thanks for attending this class. If you have any questions, feel free to email us, and I'll see you guys on next Thursday. All right, have a good day.